today's speaker, who is Henniart, who will speak on the Satake Isomorphism Mod.p.
So let me first thank the Institute and the organizers of this special period for the invitation to come and spend some time here, and also the organizer of this seminar for the opportunity to report on recent work. This is joint work with Marie-France Vigneras, and my apologies for those of you who've heard either Marie-France or myself talk about this subject before somewhere else. So let me first tell you about the context of this work. The general context is the study of smooth, irreducible representations of local reductive groups but with non-classical coefficients, say coefficients in a field of positive characteristics. For example, a finite field. So a little bit of notation. In the sequel, F will be your favorite locally compact non-Archimedean field. So as usual, the ring of integers will be denoted by O. You have its maximal ideal. The residue field will be K. And we assume, well, that the characteristic of K is a fixed prime P. We also fix, maybe after this goes up, a connected reductive group G underline over F, and we look at its group of points, which I call just G, and I will use similar notation for other reductive groups over F. And this is a topological group which has the feature of being locally pro-P, in the sense that there is an open subgroup which is a pro-P group, pro-finite and pro-P. So, for example, if G is GLN, as an open pro-P group of GLNF, you can take the matrices which are congruent to 1 modulo the maximal ideal. So classically, so I want to recall a little bit of a classical theory where the coefficient field is the field of complex numbers, just to make the contrast with what happens when you have coefficients, a field of positive characteristics. So classically, one studies smooth, irreducible representations of G on a C vector space. So such a smooth, irreducible representation is just a homomorphism of C into the automorphism of the vector space V, which is usually infinite dimensional. And smoothness means that every vector in V has an open stabilizer in G. Irreducibility is this usual algebraic notion. In particular, you see that since every vector V has an open stabilizer, every open subgroup, provided it's small enough, has non-zero fixed vector, provided that V is non-zero. So what is known? Of course, why do we study that? We're forced to study that because such representations, smooth irreducible ones, are local components of automorphic representations of a reductive group of a global field. And being interested in number theory, you have to study those, right? So what is known is that if V is a smooth irreducible representation, pi V is a smooth irreducible representation like that, and K is an open subgroup of G, then the space of fixed point here is finite dimensional over C. This is a theorem. So this says that pi v is admissible. Admissibility means that you have such a finite dimensionality for every open subgroup K of G. And this subspace Vk is acted upon by the so-called Hecke algebra H, G, K, C, which is the Hecke algebra of double cosets. So let's say in K, G, K with coefficients in C with a convolution operator, natural convolution multiplication. And what is known in this context is that if Vk is non-zero, so K is small enough that Vk is non-zero, remember pi is smooth and irreducible, and in particular V is non-zero, then H of G, the module Vk, is a simple H, G, K, C module. And even more, in this way, you find a bijection between simple H, G, K, C modules up to isomorphism on the one hand, and irreducible smooth representations, complex representation of G with Vk different from 0, and again up to isomorphism. So the study of this algebra and its module category gives you quite a lot of information about this smooth representation theory of G. Of course, you would have to vary K. Okay, now, well, this past decade or so, even before, the study of congruences between modular form has had quite a number of successes in number theory. And following the lead from modular forms to automorphic forms to representation theory to the local part of representation theory, this forces us to study such smooth irreducible representation, actually smooth, maybe not irreducible, as occurred in yesterday's talk. But let's concentrate here on the smooth and irreducible ones, of V on a vector space over some coefficient field, which is possibly a finite field of positive characteristic. And here I would concentrate on a special case, which is more difficult, in a sense, the case where C is a coefficient field, but C has the same characteristic P as the residue field of F. So exactly the same. I have no assumption on C. It could be finite or algebraically closed, or the algebraic closure of the finite field, Fp, whatever. And C doesn't have to have any relation with K. They are just unrelated objects. Only the characteristic is the same. So there is the number, in that case, a number of new features which intervene. Some are good, some are bad. The first one, which is possibly good, is that if, let's say, K plus is a pro-P subgroup of G, and pi V is a non-zero smooth representation of G on a C vector space, then it has fixed points. So this is quite interesting because, for example, you can take a rather large pro-P open subgroup in G, and you assume that because this group is rather large, if you look at those fixed points, then you will have quite a lot of information. Well, it may be not quite large enough because it's a pro-P group. For example, you would like to take here, instead of 1 plus Pn of P, the group of integral point of GLN, but this is not a pro-P group. Still, this group of integral point normalizes this subgroup and consequently acts on the fixed point space. So if you have such a K plus, the normalizer of k plus in G certainly acts on Vk plus and also any intermediate subgroup. So you could take, for example, a compact subgroup in the normalizer containing k plus. Well, there is a problem here, is that in the classical case, you know that irreducible and smooth implies admissible. In this context, when the coefficient field has characteristic p, it's not known. Not known if pi irreducible smooth is automatically admissible. So in the following, I will look only at irreducible smooth admissible representations. Anyway, they are the more interesting ones, and the ones that come from geometry usually are admissible or nearly admissible. So now you have a assuming admissibility, you have a finite dimensional vector space, Vk plus, on which, say, k here acts. So you can find in Vk plus, there is an irreducible subrepresentation of the group k, trivial on k plus, let's say rho w occurring. Now if you fix such a rho w occurring, this means simply that what I would call V of rho, the homomorphism of k of rho into V is non-zero. But this space here is a module over a Hecke algebra, or what is called an intertwining Hecke algebra, is a module over an algebra H, G, K, W, let's say. This is my notation. This is an algebra of functions, say phi from G to the endomorphism of W, which are compactly supported. I don't know if so I will assume that K is compact from now on. One can deal with more general groups like compact mod center, but compact subgroups will be enough for my purpose. Compactly supported, and verify two intertwining properties, that f of k, phi of kg is rho of k composed with phi of g, and phi of gk is phi of g composed with rho of k, when k is an element in this compact subgroup and g is any element of g. And the, well, I guess I have to erase something. The multiplication in this algebra is a simple convolution. Given by a simple convolution formula where phi convolved with psi evaluated at a point G is simply the sum over h and g mod k of phi of h psi of h minus 1 g, and you verify instantly that the sum indeed depends only on the class of h modulo k. So the goal is to investigate the structure of h, g, k, w, at least when k is taken to be large enough so that you can really expect that this structure is interesting. But anyway, you know that you can take it large enough. Any pro p, k plus will do. So its normalizer, at least the compact part of its normalizer, will do too. So it will turn out actually that those algebra are very often commutative. And so such an investigation was started for G equals GL2 in the 90s, I think, by Bartel and Livne. but our work was very much inspired by a recent paper of Florian Herzig treating the case where G is an unramified group and K is a hyperspecial maximal compact subgroup. So this implies, for example, if G is a Chevalier group over Z, and you take K to be the group of integral points of G by work of Herzig. So, I mean, it's only work of Herzig which made us think that maybe there was something general behind that. But I have to give a warning here. Life is not that easy. If pi v is irreducible smooth, so over this field of coefficients here, C, v of rho, if it's non-zero, is not necessarily a simple module. That's the first point. And also, it does not necessarily determine V up to isomorphism. So in this positive characteristic case, the situation is not so clear. I mean, if you have information about this intertwining Hecke algebra and its module category, it doesn't give you so much information about the category of smooth representations of G, for example, or even smooth irreducible representations of G. And for G equals GLN, Florian Herzig had to work quite a bit more to get a complete classification of the representations of GLN, smooth irreducible representation of GLN, parallel to the one of Shelevinsky in the classical case. But I will not enter that. I mean, we're just doing the tiny bit part at the start of Herzig's investigation, that is describing those intertwining Hecke algebras. So the result. Yes, I have time. I want to state my main result, and for that I have to fix a number of other notation. I will go to this side and try and use only the central blackboard afterwards. So we have, of course, to make use of the fact that we have a reductive group. So I fix S a maximal split torus. In G, Z will be its centralizer in G, so it's a minimal Levy subgroup. Say N will be its normalizer, so that N divided by Z is the Weil group of S in G. What do I need? I need also to fix a minimal parabolic subgroup B of G with Levy component Z. I'm sorry, Z is not the center, but this is notation which is used by Bruantitz, and Marie-France convinced me that I should keep Z and not put L or whatever else. And unipotent radical U in this. And of course, I will use notation like Z is equal to Z underline of F, etc., for other groups, which are then locally pro-P groups with their natural topology. So at the beginning, let's just take any open compact subgroup K of G and assume just true properties. One, that you have the Iwasawa decomposition G is equal to bk. This means already that k is big enough. And second, that you have that k is in good position with respect to this minimal parabolic. That is, b intersect k is just the semi-direct product of z intersect k by u intersect k. Then, if you have a function in your intertwining Hecke algebra, so here rho w is a finite dimensional representation of k on a C vector space, as previously. Previously, it was actually trivial on k plus. I may assume that it's trivial on k plus here. If rho is irreducible, it will be automatic. But anyway, for now, it doesn't play any role. And z, an element of this minimal Levy, put S of phi of z to be equal to the sum for u varying in u divided by u intersect k of phi of zu. So phi of zu, remember, it's an endomorphism of this finite dimensional vector space W, but I want to restrict it to the part which is fixed by the group u and intersect k. So this is, a priori, S of phi of z is something which is a homomorphism over C of W u intersect k into W. So just in this rather abstract setting, you can prove the following right away. You can prove it just by formulas, but we also have a more abstract nonsense proof, which is more pleasant to us. So let's put it as a proposition. First, this homomorphism of W fixed point under u intersect k into W actually takes values in the fixed points. This comes out of the formula and the invariance property of phi. It's not very difficult. So actually, S of phi of z, I can view it as an endomorphism of this subspace V fixed under u intersect k. And second, so phi goes to S of phi, where I see S of phi of z as a S of phi as a function of z with values in the endomorphism of this smaller vector space here, gives an algebra homomorphism of h, g, k, w into h, z, z intersect k, w, u intersect k. Since z intersect k normalizes u intersect k, you still retain an action of z intersect k on this subspace here. So you can define in exactly the same manner the convolution intertwining Hecke algebra. Okay. Well, I have perhaps to explain, this is the formula that Herzig uses, but I have to explain where it comes from and maybe why this S is for Satake. So this will take us back some 50 years or so. So why is S for Satake? Well, just for a moment for this digression, let's go back to the classical case and retain the same hypothesis on my groups. G is equal to bk, and b intersect k is decomposed in this way. Then Satake defined a map, classical, let's say, from h, g, k, c. So here I take trivial coefficient with the field of complex numbers into h, z, z intersect k. C, of course, I don't have to take fixed point, everything's fixed here, defined by the formula as classical of phi at the point z is delta of z to the 1/2 integral over u of phi of zu du. Here, du is a hard measure on u, and delta is the modulus character of b, which is trivial on u. You can restrict it to z. So clearly, let's just lower this down. This summation here is just the equivalent in our more discrete context of this integral here. Of course, there is a twist here by this delta character, which makes no sense in our setting because delta has values powers of p, and this would make no sense here. And to take p would be 0, and p minus 1 doesn't even exist. So I have to retain that. Well, the point of putting this delta in the classical setting, delta was there to ensure that, at least in the cases that I will state later, where you do have a description of this Hecke algebra, that S of phi is invariant as classical of phi, is invariant under the natural action of the Weil group, W0. So we're missing this part here, and we'll be missing any action of the Weil group in the result. But still, I mean, it's clearly the analogous thing to do. So now, which group do we take? The goal would be to take groups such that this homomorphism, Satake homomorphism, is injective, and such that we can describe the image. Otherwise, there is no point. In this general setting, there is no reason why it should be injective. And I guess it doesn't even make sense in this general setting to know, to say what the image is. So I erased something I should not have erased, but it doesn't matter. Which groups? So, well, I have to go to more notation. Let B be the Brouatitz building of the adjoint group of G over F. So to S, which is a maximal split torus inside of G, there is an apartment A in B attached to S. And in this apartment, I choose a special vertex this A, and K will be, in the following, the parahoric subgroup as defined by Brouatitz attached to this special vertex. Well, I don't want to enter here more into the Brouatitz theory. Let me just say how they interact with our investigation. Special, in particular, is there to ensure the Brouat decomposition, G equals to BK. The fact that you take a special vertex inside this apartment ensures the decomposition 2. In A ensures B intersect K is equal to Z intersect K, U intersect K. But of course, they have a number of other very interesting features. What shall I need later? So if K is such a special parahoric, Z intersect K is actually normal in Z, and Z divided by Z intersect K is a finitely generated abelian group. So it's not so bad. Even though the group might not be quasi-split, I mean, this is still. And all those facts, by the way, are due to Tom Haynes and Sean Rostami, who investigated the same situation but in the classical setting. And we use mostly their techniques for the combinatorial arguments that we use. So all these things are due to them in the context of K being a parahoric, special parahoric subgroup. But here we want to have a bit more this representation rho, which intervenes in the Hecke algebra. And there again, there is a special feature of parahoric subgroups. Let K plus be the pro-P radical of K. That is the maximal normal pro-P subgroup. There is one, it's unique. And it turns out that because of Brouatit's theory, K over K plus is naturally the group of points over K of some reductive group, which I denote by G-red, even though it's not very good because it does depend upon the special points I've chosen. But over the residue field K, inside of K divided by K plus, you have actually a similar decomposition with intersection with K plus, similar to this one, and Z divided by Z intersect K divided by Z intersect K plus, which is a subgroup of this, appears as a maximal torus, the group of points over K of a maximal torus in G red of K. And guess B intersect K divided B intersect K plus is a Borel subgroup with this thing as a Levy component and with unipotent radical U intersect K divided by U intersect K plus. So you find yourself in a situation where you have a nice connected reductive group. I should point out this connected reductive group. This is why I've taken the parahoric subgroup. If I had taken a bigger group, like a maximal compact special subgroup containing the parahoric, I would still get here a reductive group, but which would not be connected. I don't know if one is allowed actually to call a non-connected group reductive, but anyway, this is quite important. And the point is that the representation theory of such reductive group of points of a reductive group over a field of characteristic P, is known. It's called, most people call that indefining characteristic, because the coefficient field has characteristic P, and the group is in characteristic P2. So we use, so the result, so maybe I have to switch there. We use results of Marc Cabane on the description of irreducible representation over C of such a group. On the irreducible C representation of. Well, I don't want to describe it now. The main point for us is that if rho v, rho w is such, so maybe I should be a little careful here because I've made no assumption on C. C is not necessarily algebraically closed, so I should add here that you take an absolutely irreducible representation, just for definiteness, not to say anything stupid, but I can also replace C by its algebraic closure, and I would not lose much. So if rho w is such an absolutely irreducible representation of K over K plus, then the space of fixed points here is always a line, is always one-dimensional. So in this context, even though it's a finite reductive group, there is no cuspidor representation unless you're with a torus, really. With a torus. It's always one-dimensional, so in particular it's non-zero, and of course, Z intersect K acts on it via a character, because it's one-dimensional, which I call chi V, chi W, or chi simply. So it's a character into C cross, which of course is trivial. On Z intersect K plus. And now I can state our main result. In this situation, so K is this special parahoric, the Satake map, which I defined previously, is injective, and we know its image. So this theorem gives some description of the intertwining algebra Satake map HGKW into H Z intersect K W fixed by U intersect K is injective, and its image is made out functions supported on negative or anti-dominant element. Z in Z is anti-dominant if, well, the conjugation by Z minus 1 contracts U intersect K. So if you stay in U intersect K by this conjugation. It's rather a matter of convention of expressing it this way. So this is the main result, but to show you that it tells something, maybe I should have some more comments and maybe complements. Several comments are in order. First, when G is unramified and K is a hyperspecial compact subgroup, then it's due to Florian Herzig. And we're just following his lead here. So in the classical setting, remember you had this map S classical with the delta, where Haynes and Rostami in exactly the same context with the special parahoric subgroup established that S classical gives an isomorphism of this Hecke algebra for K, for the parahoric subgroup, and the set of W0 invariants in this small Hecke algebra here, which actually is commutative, because I told you that Z divided by Z intersect K is a finitely generated abelian group. Well, in this theorem, you can actually replace K by a bigger group. It implies the same theorem for a slightly bigger group. For example, a maximal special maximal compact subgroup containing K. And in that case, this is really very classical. It goes back to the pioneering work of Satake in the 60s, and then, maybe Brua. In Brua's thesis, there was examples too, and then Bruhatitz and Cartier, for example. But this is rather recent. It's 2009, Tom? Yeah? So maybe now I can erase those notations. So I have other comments. This is a whole part of comments. So let's look a little bit at the target algebra, this algebra here. I shall put here the character chi, because after all, this is one-dimensional, and all that matters is this character chi. Up there, thank you. I need to look at my paper of the blackboard, and my eyes are not so good, really. Thank you. So I told you that Z intersect K is actually normal in Z, and the quotient group is rather nice, and also that Z intersect K plus is a torus, it's a prime 2p group. Actually, the group of points of a torus over K. Now, so since this is normal, double cosets are just single cosets, so let's take X in Z, look at this coset here. When does it support a non-zero function? Well, remember the defining relation where something like chi phi of xz is equal to chi of x phi of z for z in z. And the same thing on the other side, phi of zx is equal to phi of z chi of x for z in z. Those are the defining relations. And you see immediately that x supports a non-zero function here if and only if x belongs to what I would call z chi. It is the stabilizer of chi in z. This is a subgroup of z of finite index in z. Now we can investigate right away too the commutativity of this algebra. Indeed, if you have such a function, so for x in z chi, let tau x be the function in the algebra with value 1 at x. 1 seen as an endomorphism of this one-dimensional vector space here. Well, you have tau x, tau y is equal to chi of x, y, x minus 1, y minus 1, tau y, tau x. It's an immediate computation that you can do. And this makes sense because remember, the group z divided by z intersect k is abelian. So this is in z chi, x is in z chi, y is also in z chi. So the commutator is in z intersect k, and you can take chi of it. So this makes sense. So you have a criterion h z intersect k chi is abelian if and only if chi is trivial on the commutator's subgroup from z chi here. So as it turns out, we struggle to find an example where this algebra was not commutative. At first we thought that it was always commutative. So, but you can devise examples where it's not commutative. If I have some time left, I will give you one. But in the interesting cases, this algebra is commutative, and consequently, the Hecke algebra for G, the intertwining Hecke algebra for G, is also commutative. So let me state it as a proposition. H, Z, Z intersect K, chi, and consequently, H, G, K, W is commutative in the following situations. All of it is not entirely written, so maybe you should take that with a grain of salt, but if I have time, I write that here. So, of course, a trivial case is when chi is trivial, because the criterion is obviously satisfied. A second trivial case is when G is quasi-split, because then Z is commutative, being a torus. Then there are less obvious cases when G is split over an unramified extension of F. It also works when G is semi-simple, simply connected. Also when G is semi-simple but of a joint type. And it works also when G is classical, by which I mean an isometry group or similitude group for a quadratic, Hermitian, or symplectic form, even over vector fields over division algebras. So that works in those cases too. So in most of the interesting cases, really this algebra is commutative, and we can hope to use the easy representation theory of commutative algebra. So another comment on the structure of the, not this algebra HZ, but on that one here. So maybe it's the fourth comment. I told you that Z divided by Z intersect K is finitely generated abelian group. If I call Z minus the set of anti-dominant elements in Z, then Z minus certainly contains Z intersect K. It's a monoid under multiplication, and the quotient here by this monoid, by this invariant subgroup, is a finitely generated monoid. You have to look at the way that Z minus is defined and use classical results on convex polytopes. As a consequence, one has to work a little bit. As a consequence of that, you have some nice structural properties of this Hecke algebra HGKW. HGKW is a module of finite type over its center. And this center is an algebra of finite type over C. So even in the non-commutative cases, this is not so bad. few minutes for an example. So let me say just a little bit, not about the proof, but about the fact that the image of S of phi for any phi, vanishes on the non-antidominant elements. To me, this is a reflection of the fact that to get, in the classical setting, the Satake map to be invariant under W0, you have to add this delta. And if you think that this delta somewhat survives here, you see that for elements which are not antidominant, you have to correct by multiplying by a power of p, a positive power of p, which becomes 0 by reduction. So this is some explanation. Of course, not a proof at all, but it is some explanation why you have such a vanishing. Okay. So now maybe I still have a few minutes, right? So I can give you an example. I will not be able to work out this example, but I can tell you the shape of it. So an example where the algebra is non-commutative, of course. So you have, in this example, actually, of course, G is equal to Z. It's enough. If we can do that, that's OK. And of course, you have to avoid a number of situations which are more or less the ones you would try first. So in this example, let's take K to have 3 elements. For example, F is equal to Q3. But we can devise an example over any base field F. It's just a bit more complicated. So E over F will be a quadratic ramified extension. And I will write Y goes to Y conjugate for the Galois automorphism, the non-trivial Galois automorphism of this. OK? One more data. D over E would be a central division algebra over E of degree 16, so reduced degree 4, and invariant, well, there's not much choice. Let's say I take the invariant 1 over 4. So the group G will be such that G, the group of points, so which is our group G, is the set of D xy in D cross E cross E cross, such that n of D x square y over y conjugate is equal to 1, where n here is the reduced norm from D cross to E cross. So this equation is in the elements in E cross. Maybe I should write it a bit larger, because it's not so obvious to see it. The equation is norm of D x square y divided by y conjugate is equal to, yes, so G of is equal to D x y in D cross, E cross, and E cross, such that you have this equation. Now, if you look at the way of course, this is compact mode center. There is only one parahoric subgroup. So I just have to tell you what it is. It's simply the intersection of G with UD cross UE cross UE. So you take unit everywhere. And K plus is just the intersection of G with 1 unit. So that K over K plus appears as the set of Z, T, U in the multiplicative group of residue field of D cross the multiplicative group of residue field of E, which is the same as K because I've taken E to be ramified over F. So it has 3 elements, and this one, well, this multiplicative group has just 2 elements, and this one has 80 elements, such that, so what happens? You have a norm from KD to KE. You have T square, and this U over U conjugate disappears because it doesn't show up in reduction. So this is one. Yeah, I will not be able, as I told you, I will not be able to give you the proof, but at least I can state something. Proposition. Let's take C equals to KD. Why not? Anything bigger would do, of course. And epsilon from KD cross to C cross be a character of order exactly 40. We call this is of cardinality 80, so it's just the order is just a little bit smaller, the maximal one. Let chi from G to C cross from, well, for GS from G or from K over K plus to C plus be defined by chi of this thing Z TU here is equal to epsilon of Z. So it just depends upon the first component. Then the algebra G K chi is non-commutative. What happens actually is that the stabilizer of this group K is all of G, but K is non-trivial on the commutators of G. Of course, this is devised exactly for giving a counter example. So I guess I'll stop here. Thank you very much.